as our first speaker, and he'll tell us about Fourier analysis and in general analysis of the high dimension expanders. So take it away, Max.
Great. Okay, great. As Dor said, I'll be talking about extending the theory of analysis to high dimensional expanders. I want to give maybe a slight overview of what I'm going to talk about in these two lectures and a slight disclaimer. So the first thing that we're going to do is we're going to try to extend sort of this core theory of having a Fourier decomposition and sort of L2 or spectral based properties that we discussed in the last couple of days. And we'll see a beautiful basis due to Diksha, Dinner-Filmus, and Harsha that we'll focus on constructing in the first lecture. In the second lecture, will actually be largely independent from the first. We won't explicitly need the tools that we develop. We'll talk a little bit about properties beyond a spectral case, things like hypercontractivity that was mentioned yesterday, and we'll see how high dimensional expanders are related to this type of behavior. That we won't sort of prove this explicitly. Okay, so let's start. Where's the black marker? So just as a reminder, I think people probably do not need this at this point, but what I'm going to do is write up sort of the properties of the Fourier decomposition that I would like to generalize to high dimensional expanders. So we all know very well at this point, we have a function on Boolean cube. I'm going to use k as dimension in this talk. If I write something else, please catch me. People use lots of different things for dimension. This is usually the one that's used in HDX. So if I have some function mapping the k-dimensional cube to the reals, then of course it has a Fourier decomposition. And moreover, we saw that it's typically useful to divide this into levels corresponding to the sides of the set S. And in some sense, this is, F, we can write Fi is equal to the sum of sets of size I at S. Chi S, and this is sort of the contribution coming from level I. This is the Fourier degree at level I. We talked about this. And largely, this is sort of we're going to look at generalizing these types of Fourier level functions. So there are sort of three properties that I'm going to care about. First is sort of a moral property, which is basically what I just said. I'm going to want that this function Fi in my decomposition sort of comes from level I combinatorially somehow. This is like the degree or level I part of F. Here, this is sort of literally the case, right? This is coming from the sum of I juntas, these characters that only depend on I coordinates. When we move over to complex land, which I'll be more explicit about, these will be like functions that sort of come from the I sets, that come from level I of the complex and get lifted up to level K. Okay, the second and third thing are maybe a bit more explicit. We want orthogonality, or at least approximately. Just write orthogonal. So we want that Fi Fj is equal to 0 as long as I is not equal to j. And this implies some version of Parseval's theorem, which we saw was very useful, right? So this was just saying I can express the standard 2 norm of F as, I'll write it as just the sum over these level functions. If you expanded this out, you get the sum of the squared Fourier coefficients, but this is sort of a coarse version of Parseval. So we'll want to generalize this. And finally, this is a property that Noam talked about. We'll want our basis to be an eigenbasis with respect to certain operators. In particular, Noam talked about this with respect to the noise operator, right? He showed that applying this to a character of size I got you an eigenvalue of rho to the I. In particular, if we apply it to level I, we got that T rho of Fi was equal to rho to the I Fi, and we saw how this sort of dampened higher levels and how this was very useful. So we'll want to maintain this behavior. The noise operator is a little bit more complex to represent on high dimensional expanders. You can do it, but I'll want to largely focus on a simpler noise process, which just corresponds to the hypercube graph, where I pick one, instead of picking each coordinate and resampling it with some probability 1 minus rho, I'm going to pick one random coordinate and resample it. So this is like the lazy hypercube graph, where I have Hamming distance 1, but I'm adding some laziness, allowing myself to go back. So I'll write this as like q tilde of k. It's the lazy hypercube graph, and you can show basically by the same proof that Noam went through. I'm not going to go through it explicitly since it really is the same thing. This is also, these are both Cayley graphs on this object. So you can also think about it this way. They're eigenvectors. And this will have eigenvalue. You can check yourself if you want. K minus I over K times Fi. And I'm being a bit explicit about this because we will see these appear again later in the talk when we move to high dimensional expanders. Okay, so this is the three properties that we're going to try. Hopefully at the end of the talk, we'll have some basis that satisfies these at least approximately on high dimensional expanders.
This technology, you can go from this QI tilde to QO by taking a small number of steps. So, yeah.
Oh, yeah. Yeah, that's true. Yeah, okay. Are they exactly equivalent to this? Oh, okay. I didn't realize this. Yeah, we'll see that you can also define it by looking at like convex combinations of longer replacing many things throughout the complex, which is typically how I think about it. I didn't. Okay. That's useful. Okay, so now I want to, unfortunately, spend a little bit of time on background on high dimensional expanders. Again, Arit went through this yesterday, but I think at least for me, the first time I saw it, I really didn't get it. So I want to make sure everybody really is on the same page, and I'm going to go through it again. Also, I didn't say this, but please, people interrupt and stop me when you don't understand something or have things to say. Okay, so let's recall high dimensional expander definitions. This will include, like simplicial complexes, these random walks and operators that Arit talked about, et cetera. We'll go through all of this. So first of all, we're going to focus on a simple case of what are called pure simplicial complexes. So a pure simplicial complex X, just as Arit defined it, is basically just a downward closed hypergraph. And I should say, we'll do K dimensional. I am unfortunately going to depart slightly from the notation that we had yesterday, because in our world, which is not topology, K dimensional things have K coordinates. In the topology world, K dimensional things have K plus 1 coordinates. I am going to use the notation that X is this collection of subsets where the top level XK is truly subsets of size K, not of size K plus 1, to be very explicit. So we don't have confusion about this. So XK is just some K uniform hypergraph. Let's maybe write sort of on n vertices. This will just be some subset of n choose K. And then all of the lower levels, so we can also see this sort of in this diagram over here, which I'll pull over in a second. All of the lower levels, Xi, are just given by downward closure. So Xi is all of the I sets that is something that's contained in Xk. So Xi by downward closure. And people will typically draw simplicial complexes as, I guess this is called a Hasse diagram. I haven't drawn in the edges. So X0 will be sort of one point here, which is the empty set. And then we'll have X1, which is, I haven't labeled these, but these are like the vertices. So this is like 1, 2, over to n. And then these will just be all the sets in the complex. And you can draw edges in this diagram by inclusion. And you can look at these things like the averaging operators that Arit talked about as moving between levels on this diagram. And we'll sort of move back to here when we define things and see how the picture looks on the diagram. For me, that's the easiest way to think about all of these things. Okay, so this can always be expressed as this diagram. I'll mention in general that people really work, Arit said this too, really work with weighted simplicial complexes where there's some distribution of the top. For this talk, again, I will do the same thing that Arit did. We'll assume everything is super regular and that all the distributions are uniform throughout. And maybe in the next talk, we'll look at a case where this isn't true, but here we'll focus on this simple case. Okay, so now I actually want to define the averaging operators. I guess if I move this over here, people can still see at least the top levels of this. Yeah, I realized too late that this got cut off. Okay, so now let's talk about sort of functions on complexes. So we call a space of functions mapping I sets on the complex to the reals will be denoted by CI, or CIXR would be the right way to do it. So again, this is just functions that apply values to each of these dots in the diagram. So f sort of lives on this level in the picture. Okay, we can move, or sorry, I guess I should say that this is an inner product space. So we can look, we can define the inner product between two functions on level I. Just as you would expect, this is the expectation over an I set drawn from the complex of f of tau, g of tau, and we'll define norms associated with this space. And again, for simplicity, think of these as uniform, even though maybe really they're not, but we can sort of always ignore this. And then we can move functions up and down levels on this complex by using what are called the real valued boundary and co-boundary operators, or the averaging operators, some variant of this. So the averaging operators. We have the down operator, di. So I'm going to keep basically the notation that Arit used, which is this index will tell you the input level of the function. So this maps a function on at level I down to level I minus 1. So di of f will live on one level below in this picture. And this is just given by sort of the only thing you could naturally do, right? If I want to know the value here, I'm going to average the value over everything that contains this in my diagram. So it takes this average over sort of the length or this local part. So this is the expectation of f of sigma. Oh, sorry, forgot to write di of f of tau is equal to the expectation of f of sigma, such that sigma contains tau. So I guess sigma is drawn from xi, and to be explicit here, sigma is of size I, so sigma lives here, right? The function lives here. We have to sum over things on this level, and tau lives one level below that we're getting the value of. Okay, similarly, we have the adjoint operator, this, which lifts up on the complex. So we have the up operator, and we'll do I minus 1. Sorry, so this should be I minus 1 to I, and this is just defined to be the flip of this. So u of I minus 1. I wonder if there's a better, can people see this, or should I move to a better marker?
Better marker would be great.
Better marker? Okay. Oh, you have the cable try. Thank you. Great. Okay, so we have the adjoint operator. Thank you, that's much better. Ui minus 1. So now we're taking a function that's on, maybe I should say f prime. So we'll have some f prime that's on this level. And now this will take in, so this lifts the level ci. So this takes in, when I have ui minus 1 f prime, it takes in a value, say here. And again, we do sort of the only thing you could think to do. I average over the values one level down. So now I'll look at the expectation over f of tau, such that tau lies in sigma. And now tau is in still in xi minus 1. Okay, and Arit proved that these operators are adjoint to each other. And I'll actually want to do a little bit more than this. I don't think Arit mentioned, but I could also compose these operators, right? If I wanted to move, say I had a function here, and I don't just want to lift it one level, I want to lift it all the way up to the top of the complex. I can repeatedly apply the lifting operator. Let's say I actually started at this level, then I lift this to UIF, and then UI plus 1, UIF, etc., all the way up to the composition, lifting this up to the top level. And how does this act? It's still just this averaging process, right? This what's the value of the lift to this function on xk? I'm again just averaging over all the possible values that are below it in this diagram, right? So I'll also define sort of these composed averaging operators. So
your averages here, those are induced from the distribution at the top level?
Yeah. So in reality, there's a distribution of the top level. I induce distributions below, and these are all with respect to the appropriate distribution. Yeah, but we'll pretend for simplicity everything's uniform. So I'll write these just notationally. UKI will be this composition that lifts functions from level I to level k. So this is the composition of UK minus 1 through UI. And similarly, DKI is going to be the function that the operator that takes a function up here and lowers it all the way down to I by repeatedly lowering. And this is the opposite. This will be dk down to di plus 1. Okay, so these are the composed operators. Maybe I'll move back over to this board. And now we discussed how we can compose these operators to get a series of random walks on the complex, which I think typically people call higher order random walks. I don't quite remember what Arit called them, but the basic version of this, and the one that we'll mostly focus on analyzing, is the lower walk, which is UK minus 1 dk, which starts at a function, or you're thinking about it as a random walk. It starts at some k set up in xk. It moves down by removing a uniformly random element in sigma, and then it moves back up to level k by adding in another vertex, which completes to a k set in the complex. So this is what's called the down up walk. I think we'll probably hear a lot more about this and related things in Quiqui's talks, but it'll also be very important for us. So I'll note, again, we can use these compositions to make longer and different walks in the complex, right? So I could also look at UKI, DKI, and this would be a similar process where I walk down to level I and back up. And if I wanted to do something like generalize the noise operator, I guess either I could do this Poisson process, which I hadn't thought of, or you can take a convex combination of these longer walks, and I'll maybe state as an exercise that you can generalize T rho as something like k choose I, rho to the I, whatever, some binomial distribution of the set size of the set that I'm resampling times this longer walk UKI, DKI. Okay, don't worry too much about this if you don't follow. Largely, we'll just focus on this walk, which is simpler. So then the last thing that I want to do here, I actually want to look at this walk on a particular complex to show you that it's something that we're very familiar with and that we've seen before. I'm going to show you what this looks like on the hypercube, which hopefully people in the last few days have seen. So I can think about the hypercube. I can think about this as a k-dimensional partite simplicial complex. If I want to be formal about this, then what's x1? This is the set of vertices. For each coordinate, I'm going to have sort of an appended thing that stands for the color. So it's going to be like 1, and then this will be cross 0, 1. So these vertices will be basically these pairs, where here is a coordinate 1 through k, and here is a bit 0 or 1. And then what I get is actually, when I look at xk, is actually a complex that Arit mentioned, which is the complete multipartite complex. What I do is I take all possible combinations of k vertices that have one of each index, right? And this really does just give the hypercube. And what happens if I apply this down-up walk to the hypercube? Well, this is exactly the process. I'll cheat a little bit. Say I'm at some k length string. Again, really, what is this? This is actually like 1, 1. This is actually 2, 0 in my simplicial complex land, but I can sort of just phrase it like this. What does the down-up walk do? It picks a uniformly random one of these elements, so a uniformly random bit in my string, and then it removes it. It moves sort of down one level, and then it resamples a possible vertex that completes to something in the complex. Well, I only have two options. I have to replace this coordinate. So I replace it with 0 with 50% probability and 1 with 50% probability. And this is exactly this lazy hypercube graph. So the sort of theory of higher order random walks, and if we went through this theory explicitly, we would indeed see that the noise operator on the cube gives you the noise operator back. So there's a true generalization in terms of these sort of Cayley type noise operators on the cube into general operators on simplicial complexes, or even, as Arit mentioned, to more general types of posets like the Grossman and objects like this. So we'll basically focus on the simplicial case for this talk. Okay, I think the last thing that I'm supposed to do here is I haven't reminded you what a high dimensional expander is. So let me do that, and then we'll finally get to building a function basis. How am I doing on time? Okay, I think we're fine. Okay, I'll erase that.
Very quick question.
Yeah.
What is the SI? How does that relate to?
Sorry, S is supposed to be the index. So this is like the coordinate 1 through K, and this is the bit value of the coordinate. So you need to have one of each index and then anything of 0 or.
So x1 is k times 0, 1? Oh.
X1, yes. Sorry.
Okay.
Sorry, what I meant to write was the union over, sorry, I equals 1 to K of I cross. Thank you. Yeah. Right. So each of these should have an index 1 through K. Thank you. Good catch. Okay, let me remind people what high dimensional expander is. I'll erase this because we're going to rewrite a theorem that says basically this in a couple minutes. Okay, so we had two definitions of high dimensional expanders that Arit mentioned. In this talk, we'll actually only need the random walk definition, but in the next talk, we will need the local spectral definition. So I'm going to give both here, and then next talk, I'm not going to repeat the local spectral definition. So I lied slightly about the talks being completely independent. Definition, X is formally you'd call this a gamma local spectral expander. I'm just going to call it a gamma HDX. All right, one-sided HDX. I'm now realizing I needed to define links, which I didn't do. So let me here where we had a simplicial complex define links for people. So this was one of the main definitions that Arit went through. So I'll go through it a little bit more quickly. So given a subset S in the complex, it can come from any of these levels. The link X of S, you can again sort of view it over in this diagram. Like say I have something in some S in level I, and I want to take the link. One way to think about this is I look up in this diagram at everything that contains S, and then I remove S. That will give me a lower dimensional simplicial complex that's called the link. So slightly more formally, we can write this as all T in X, such that T union S is also in X. So you can also write this as like T union S without S, which is what I said over here. So these are the links, and if you're in a distribution world, there's some induced distribution on here. Again, we'll just assume it's uniform. So X is a one-sided gamma HDX if for all subsets in X of size at most dimension -2, then the graph, the underlying graph XS1, XS2 is a one-sided gamma spectral expander. Okay, so this was the original definition that Arit gave of local spectral expansion. It's probably currently the most common definition of spectral high dimensional expansion that's used. And then Arit introduced the second definition that used the random walks. Maybe let me say briefly, Arit also looked, so we looked here at the down-up walk. You can also, of course, look at the up-down walk. maybe I shouldn't be at the top of the complex. So we can compose U and D. So we could do UK minus 1 dk. This would be the operator that starts here, walks up and walks down. And then I redefined sort of the non-lazy version of this. Let's pretend there's some xk plus 1 up here so I can keep using k. Sorry about that. I redefined the non-lazy version of this operator as mk plus. So as she noted, when you add one thing, there's a 1 over k chance that you remove it when you come back down. So this just removes that chance. And she defined this notion of random walk high dimensional expanders. She said X is a gamma random walk HDX. Basically, if for all levels of the complex, we have that the non-lazy up-down walk at level I minus is similar spectrally to the down-up walk. Is similar to UI minus 1. DI, particularly the operator norm of this, is at most gamma. Okay, and to reprove this theorem, we're only going to use one direction of it, that any gamma, I guess two-sided gamma HDX is a gamma random walk HDX. Okay, and we will actually just use this definition in building the basis. Okay, I think we now have all the tools that we need to actually build the Fourier basis.
So what is the MI plus?
MI plus is the non-lazy up-down walk. So it's I just remove the 1 over I chance of coming to the same thing. Yeah, so sorry. UD is down. Okay, this is very annoying. UD is down up. Yes, the operators are applied in this direction, but when you think about it as a random walk, this is actually the down step of the random walk, and this is actually the up step of the random walk. So if you look in like the sampling literature, you'll see this definition flipped. So this is like the function operator version of the definition versus the random walk version of the definition. Sorry, there was another question, I think.
Yeah, the question was, the other one is also lazy, but it's only a tiny.
Yes. So on it, the other walk is also lazy. And if you wanted to do this in terms of like what's called a sequentially differential poset, or like you wanted to be really careful, you would also remove the laziness of this. But you can show that in a gamma high dimensional expander, in a two-sided expander, you cannot have much laziness because you can prove that it would force the spectrum to have a large eigenvalue. So the eigenvalue here will always be like at most, or the laziness will always be at most O of gamma. So we don't have to worry about it. It's a good question.
And just for my, like the down up walk, that's representing the part of the spectrum you don't care about. You're getting rid of,
yeah, this is like generalized. If you had this on the first level, this would be like the stationary distribution.
Yes, in the grassing, I would get rid of like the constant functions for the Laplacian. That's what I would subtract.
Yeah,
that's what I'm just distinguishing the two operators. That's the up down is the part of the spectrum you don't.
Yeah, in a sense, when you're at higher levels, like it's not a trivial part of the spectrum anymore because there's like structures on, but you're sort of subtracting out the lower levels of the object. Yeah, okay, and as you say, like this is ending up with gamma, so you can think about it, yes, as subtracting out the constant part. Okay, so let's actually move to this function decomposition. Let me maybe erase this. Okay, so the averaging operators, I think, we said, or I said sort of at the beginning, that morally we want to think about decompositions by level. We want to think about Fi as being functions that come from level I of the complex. And now we really have a way to talk about this, right? We have ways to lift and lower functions throughout the complex. These are also used to define higher order random walks. And so we'll also sort of want to build this basis that acts nicely with respect to these operators. So let me make sort of like a first attempt of defining what it means to come from level I as a function. So sort of our goal here will be to define what it means to be like a level I function. Then we'll use this to build a basis. So one very natural definition is I would, if I'm trying to build a basis, I'll say for CK, for this top level up here, and I'll say something is level I if it's literally a function on level I that's then lifted up to level K, right? So the first thing that I think you would consider is, functions f that are equal to UKI GI. In other words, things that are in the image of this linear operator UKI in the complex. So this is almost what we want, but like standard techniques in building a basis, we need to subtract out the parts that are coming from below, right? This isn't really just level I. GI could have been a function that was lifted. GI could have actually come from I minus 1. We want to rule out the case. We want to subtract out everything that's coming from below. So we want to rule out this case that GI is actually a lower level function on the complex. And so to do this, we'll look at this space where we only lift functions GI, and we want to ensure that GI is in the orthogonal complement of things that come from one level below. So we're gonna force lifting functions at level I that are orthogonal to everything that are coming from below. And this has a very nice representation because so maybe I should write this over here. So the image of UI minus 1, this is something that lives on level I here. It's things that are being mapped up. Because the operators U and D are adjoint, the perp space of this image is just equal to the kernel of its adjoint, the kernel of the down operator. So this suggests the following definition of level I functions.
What's the inner product here?
The inner product, it's just the expectation over I sets. So if this is at level I, this is the expectation over I sets drawn from our complex of f of tau. And like we mentioned before, in reality, this has some induced distribution to make sure everything's adjoint, but we'll assume everything's uniform. Okay, so this suggests the following definition of level I functions.
Is that not going to cause a problem at any point?
No, it never causes it. Because you actually define, you don't actually define this to be uniform at level I, right? It's actually defined to be the distribution over level I is I draw something from the top level, and then I take a random subset, and I define everything with respect to this induced distribution. So you can think of it as every time I'm actually drawing a joint distribution from every level of the complex. Then when I talk about individual things, I'm marginalizing over this distribution. This will enforce that there's never a problem with this sort of thing.
I'm confused because you said, so when it's not uniform, there's
no, if your complex is not, it's only uniform if your complex were completely upregular. Then if you did this induced distribution, if every I set is in the same number of K sets, then it would truly be uniform and everything would work. This is not generically true. And when it's not true, the distribution is not uniform. So I'm making the implicit assumption here that the complex has regular up degree as well, which is totally unnecessary and you don't need it, but it simplifies things because then everything is uniform. So yeah, you cannot think of it as uniform in the general case.
You need it to be a design in order for things to be uniform.
You need to be a design?
It needs to be a design, yeah.
Yeah, so
at some point as computer scientists, maybe we can stop treating the uniform distribution as if it's the only thing in the world.
fair, you know what, I will say, I had a version of this talk where I did the weighted things and I was advised to throw out the weighted part of it. Yeah, I agree. But I will say you can also, for an HDX, there's a way to regularize them so that this is actually true. Well, it's not necessary. Okay, what was I doing? Space of, so I wanted to define the space of level I functions. So we'll denote this as dki. So this is the space of functions on CK that comes from level I. And this is just going to be the up operator applied to the kernel of DI, and then I'll define, because there's no down operator at the bottom level, the zeroth space here is just going to be constants. Or equivalently, this is the image of things, the lift of things at level 0, the only possible lift of the empty set is constant functions. So I can also just think of this as the image of UK0. Okay, and finally we can state this theorem, which we'll replace here.
one more time. Go over the goal and step. So we're looking at all the. All the way to the
Yeah, so this is, we're trying to decompose functions on the kth level, and we're saying we're about,
K being like an arbitrary level or like the.
just think of it as the top level. Really, you can do, I mean, I can always cut the complex off at some dimension. So I can always do this at any level of the complex. But for simplicity, think of it as the top dimension. I think you don't actually need this k plus 1. Just think of it as the top level. And we're saying the top level can always be decomposed into the part that comes from k sets, the part that comes from k minus 1 sets, all the way down the complex. And this is the theorem that I'm about to write. So this is a result due to Dick's chain in our Domas and Harsha, which raises the question of why I'm talking about it, which is essentially answers the question that we had at the beginning of the talk, that indeed this sort of decomposition exists. So to say on a gamma random walk HDX, where I think we'll force gamma to be less than 1 over k minus 1. We'll see why that's the case. We have one, that this set of spaces is indeed a decomposition of CK. So we have that CK is equal to VK0 plus VKK. So in other words, I can always decompose, equivalently, I can say, I can always write F as this sum of Fi uniquely, where Fi is equal to UKI GI, and GI is in the kernel of the down operator. So this is an equivalent way to phrase things. And I'll just mention that I made a little bit, if you're familiar with sort of building this type of Fourier decomposition, I made a little bit of an odd choice here when I just looked at sort of the kernel at level I. If I wanted to build a truly orthogonal basis, I would have made sure that I was orthogonal to sort of being lifted all the way up the complex. And you can do this. And this is studied in work of Kaufman and Oppenheim. And it gets you an orthogonal decomposition. But what it doesn't get you is this sort of really elegant formalization for how F is written in terms of the averaging operators. And we'll see that actually having G have this very simple explanation of being in the kernel of the down operator will be extremely useful. We'll see this explicitly. So just to say, you could define, we'll see, maybe I'll say for step 2 to explain this. This is not actually an orthogonal basis. It's an approximately orthogonal basis. So we'll have that Fi of Fj is less than or equal to some term in gamma times the norm of Fi times the norm of Fj. That's a lot of lines, but so it won't be truly orthogonal, but typically this is sort of, at least in this context of analysis, this is good enough. We can take gamma to be as small as we want, and so this can be as close to 0 as you want. And the third is that it will be approximately, so I should write, here's sort of orthogonality, here approximate. So it will satisfy this approximate, approximate will be eigenvectors, both of the noise operator and the down up walk, but we'll focus just on the down up walk for simplicity. So we'll have that UD of Fi minus k minus I over k. So the same eigenvalues that you saw when we applied it on the hypercube. Again, these won't be exactly equal, but they will be close in two norm. Right? So this will be, again, less than or equal to some error term in k times the norm of Fi. Okay, I have 20 minutes approximately, 15. Okay, so this is the statement of the theorem, which, I mean, I haven't shown you how to prove this at all yet, but it gives a resolution to this question we had at the beginning of the talk. So are there any questions about the theorem statement itself before I go to trying to prove it? Luckily, the proof is once you have all this machinery set up, is not so hard.
You know, like what should be the radical theorem in K?
With respect to gamma? No, there's some recent work on this that isn't on archive yet that improves. So here it's going to be horrible. It's going to be like exponent. It'll be like k choose I or something like that. this shouldn't be necessary. And I know there's some ongoing work about this that isn't posted yet, but I don't think we know maybe with respect to exactly this decomposition or exactly what the right value should be. Yeah. So this theorem will only apply to very strong high dimensional expanders. And this is something that I've been annoyed about for a while. When you look at something like the symmetric group, you can actually express it as a high dimensional expander, but at codimension J, its expansion is like 1 over J squared. Whereas I need like, if you're over Sn, you need like 1 over 2 to the n or something. So there's a huge gap in sort of weak and strong high dimensional expanders. And this really only applies currently to strong high dimensional expanders. It's not clear if that's necessary or not. Yeah. No, there's there's oh, sorry, you mean like to build a truly orthogonal decomposition. So you can make this truly zero. You can't make this truly zero. Yeah. I mean, you could just look at the eigen. There's an actual eigenbasis that would be truly zero, but I don't think the eigenbasis will actually truly correspond to these like have these nice forms in terms of the random.
It's impossible walks. Because the eigenvalues they cluster, but they're not the same. So
yeah. So this we can make zero at the cost of being very complicated. This there's sort of no hope if you want to define it like this. Yeah. Right. Yeah. The eigenvalues aren't just this anyway.
Is there a way to write down the GI, like as a projection onto something, or?
I don't know how to explicitly write GI.
You all need some expression in the UND.
Yeah, I mean, you can't. I think there is some. Somewhere actually to answer this question, I did go through and write explicitly things out to make sure that the basis wasn't orthogonal. Yeah, you can express it as some linear equations in terms of this, but I don't know like a nice like it's the projection onto this space or I don't know. And actually the fact that this is like to me, this is like the main negative of this basis, the fact that it doesn't have a nice explicit way of talking about it. And I won't get to it, unfortunately, but there are other bases based on like Efron-Stein that have a very explicit form that you can use. And those don't work as well with the random walks, but they work well with other things because they have some sort of explicit representation. Okay, but let me move to the proof so we can actually see some things since I'm running out of time a little bit. Okay, so let's first prove that we actually get a decomposition. We'll prove this guy first. So this is a fairly easy induction that will run into an issue at one step. Okay, so in particular, the base case of this is actually trivial. The base case is like a 0-dimensional complex where all I have is the empty set, and then that space of functions is the constant space of functions. So for k equals 0, the space C0 is indeed V0, 0, which is just the constant functions. This is a sort of a trivial base case. In the general setting, if I take CK, I mean, the idea is to just take, I mean, it shouldn't be that surprising from what we've done here. I can split CK into the, because dk is a linear operator, I can split this into the kernel of dk, direct sum with its orthogonal complement. And we talked about earlier that due to adjointness, this is just the image of UK minus 1, right? So again, kernel of dk lives here at level k. Its complement is functions that are being raised from one level below. So this is equal to kernel of dk, or maybe I'll write, so kernel of dk is vkk, right? This is from definition. So we've got the first part of our basis. So now this is just the image of UK minus 1. And I actually want to think about this as UK minus 1 applied to CK minus 1, right? Applied to the space of functions one level below. And then now I'm going to attempt to induct, to say I have the decomposition on ck minus 1, and I'll try to lift it to this decomposition here. So this is vkk plus uk minus 1 times this decomposition. I'm cheating a little bit of the notation, but bear with me. So by induction, this can be decomposed into these level functions. And notice that by definition, hopefully I kept it here, right? So VKI is just lifting the kernel at level DI all the way up. So in particular, or maybe I'll write here, by definition, we have that UK minus 1 of VK minus 1 I, this is exactly, this is exactly VKI, right? I'm just adding an extra U here. So if I could sort of get this to be associative and pass this through this decomposition, then I would be done. I'm writing a star here because I'm cheating. You can't actually do this. But if I could pass U through these parentheses, then I would get something that looks like this. Or I maybe should have flipped the order of these, but this would, if this magical step worked, this would complete the theorem, right? This would now be BKK, and then I shouldn't have flipped the orders, but BK K minus 1 down to BK 0. Okay, and indeed, just to get a decomposition that's not necessarily a unique decomposition, you could do this, right? There's nothing wrong with doing that if I don't want to maintain uniqueness. But in order to maintain a unique representation, I actually need this operator to be injective. And I need it to be injective at every level because I'm using an inductive assumption here. So really, the true version of this theorem says that on any complex where this up operator is injective throughout every level, then I get this decomposition. So what we have to prove is that on a Gandom random walk HDX, it turns out, as long as you select gamma to be less than 1 over k minus 1, that these operators are indeed injective. So I'll write sort of this claim which completes the theorem that on a gamma random walk HDX, UI is injective at all levels. I'm going to sketch the proof of it. I want to get to the other things, so I'm not going to be super formal. But the idea of this is to say, how do I prove this is injective? I want to show it has no kernel. So I want to show that for any non-zero function, that UIF is greater than 0, right? If I can show that this, or equivalently, remember that U and D are adjoints. So this is the same as asking that if F DUF is a positive definite operator. And the idea, roughly, is to say that I can switch between DU. Great, I still have it up. I can switch between DU and UD. I've written it slightly differently here because this is the plus version of the operator, but an equivalent way to write this, just expanding out what this is as the lazy versus non-lazy version of the operator, I can write this as DI UI minus 1. So this is the up-down walk that has the laziness portion, minus the laziness, minus for the correctly normalized down-up walk. Sorry, it's a little small. That this in 2 norm is at most I minus 1 over I times gamma. I haven't actually done anything. I just unfolded like the lazy versus non-lazy versions so that I can look at directly flipping down up and up down at the cost of this factor of 1 over I and in laziness. And now I'm basically just going to do exactly this, right? I'm going to take F du F. I'm going to say that up to some error factor in like I minus 1 over I gamma FF, that this is the same as 1 over I FF plus F UDF. So there's some error term in here that scales with gamma, but otherwise I get this laziness portion 1 over I, and I get FUDF. Again, FUDF can be written as DF DF. So this is a positive semi-definite part. So this is always greater than 0. So what I'm left with is that this guy is greater than or equal to 1 over I FF minus I minus 1 over I gamma FF. And so as long as gamma is always better than 1 over I minus 1, which we've assumed by in the theorem statement, then this is indeed truly greater than 0 and the operator is injective. So on a high dimensional expander, you always get this type of true unique decomposition. So du and ud are both positive semi-definite, because if I'm just looking at the inner product, I can trade the u to a d over here by adjointness. This is a norm. So it's always, this is like a square sum of squares. So this is always greater than or equal to 0. So I'm using adjointness of u and d to prove that they're all PSD. The trick is to show that it's actually strictly definite in this, positive definite in this case. Okay. Okay. I think I have enough time to show the basic proof for. So I'm going to prove 3 next. 2 is actually an immediate consequence of 3. You could prove it directly, but you can prove approximate orthogonality sort of instantly from this. I'll mention it at the end. Okay, I think I'm finally going to erase this poset diagram. Hopefully we've got our U set of that. Okay, so we want to prove this, the fact that this basis is an approximate eigenbasis. Let's look first at a very easy case. Let's look at VKK, which is just the kernel of dk. So if I have a function in here, hopefully it's obvious that this is an eigenfunction of the lower walk, right? In particular, this is 0. So this is 0 times f of k. And we have, at least at the top level, is a true eigenvector. Okay, this was sort of the trivial case, but it's not far from what we're actually going to do to prove the general case. And in fact, I'm just going to do v k minus 1, and the rest of the cases will follow basically exactly the same argument. So now let's say I have f in vk k minus 1. So in other words, fk minus 1 is equal to uk minus 1 gk minus 1, where gk minus 1 is in the kernel of the down operator. Right, this was the definition of our space. Now I want to look at ud k minus 1 of fk minus 1. Okay, this is equal to, I'm going to maybe drop the indices, ud u of gk minus 1. So gk minus 1 is in the kernel of d, right? The natural thing to do is now to apply the random walk theorem and flip d and u. Right, so I can replace du up to some term in gamma. So maybe let's write gamma is equal to this difference, du minus 1 over I minus I minus 1 over I ud. So I can replace this with u 1 over I plus I minus 1 over k a minus 1 over k times ud gk minus 1 plus gamma, or formally u gamma applied to gk minus 1. Right, I've done nothing in this step. I've just added and subtracted something. But now remember that gamma, this is a matrix that has operator norm at most O of gamma. And what happens here? Well, this down operator now hits gk minus 1, and this term dies. right? So this becomes 0 because this is in the kernel of the down operator. And so what I'm left with is 1 over k times just times u of gk minus 1, which is what, by definition, this was 1 over k times fk minus 1. So when I go through this process of flipping one part of d and u, I pick up a factor of 1 over k. And indeed, if I were to do this generally, but if I were to look at like I levels down, then I would flip I times, and I would get a factor of I over k. And I would continue doing this flipping process, and you gain these error terms that look like this form. But so at the end of the day, what do I have? Let's just do the k minus 1 case. So I have something that looks like this. And I wanted to say that in 2 norm, that this and this were close, right? What I was trying to prove was that UDF k minus 1 minus 1 over k fk minus 1 was small. So now I can shift this over to the left side, and I can say that this, so far what I've managed to prove is that this is indeed less than or equal to u gamma of gk minus 1. And because the operator norm of this is bounded and u is an averaging operator, so it's a contraction, this is at most O of gamma times the norm of gk minus 1. So we're almost done, except I have a problem, which is that I wanted to get error in terms of fk minus 1. And I have, yeah, Dor. Oh, 2 minutes, got it. I think I just have time to finish this. I have error in terms of gk minus 1. But we can just again apply the same trick to fix this. I want to relate gk minus 1 to what I wanted, right? Which was fk minus 1, fk minus 1. I guess people can't see here. Move over here. So fk minus 1 is u is ug is, again, I'm just going to do the same trick, is g dug. Now I flip the operators. So this this will get like a 1 over k factor from the identity of gg plus something that's like dg plus some O of gamma error term from flipping. This is 0 because again, these are in the kernel of the down operator. So I get up to some error term, a relation between the 2 norm of g, squared 2 norm of g, and the squared 2 norm of f. And so finally, I can go back to this step here, and up to including some extra error factor here, I can get that this is less than or equal to k times gamma times the norm of fk minus 1, which is what we actually wanted to prove. And if you want to do this for general I, it's really the same. The only difference is that there will be a few more u's here, and I just have to do this as many times as there are u's. It's the exact same proof. Okay, I don't have time to show approximate orthogonality, but it turns out if you have this type of behavior and you have a self-adjoint operator, I can always look at like the operator applied. I can look at the difference of ud fi fj, which is equal to fi ud fj because it's self-adjoint, but these will have correspond to different approximate eigenvalues. So this can only happen when fi fj is very small. So you can use this to immediately get approximate orthogonality, Parseval, and all the things that come from it. Okay, I'm out of time, so I'll stop here.
Thank you.
Any questions?
So I have a comment. So everything you've seen here is really work of Stanley. The only thing we did is add the gammas.
Thank you, Bob. Any more comments or questions?
So
It seems like we're developing this theory of Boolean analysis on these spectral or random walk HDXs. Reed also talked about co-boundary expansion and stuff like this. Is there an analogous theory or to be seen?
I don't know. I guess I don't even really know what it would mean to do this over F2 versus. Yeah, I really don't know. I mean, I know that there doesn't exist an analogous theory here, at least. Maybe there should be one. You can do subspaces.
So the coefficients are.
No, but that's you can do it over general posits, but everything's still real valued. Like these averaging operate. So one thing that is really nice is that this whole process, I just used this random walk thing on a poset. I didn't use simplicial structure at all. So unlike things that I'll talk about in the next talk, this all generalizes to Grossman and things like this. But it's still all real valued. All the averaging operators are real valued averages. And in coboundary, there have two sums.
Yes, but value choices. And the no.
But yeah, exactly. You map twice, it becomes zero now. So
If your coefficients are over a finite filter, this makes no sense because you don't have any option of approximation.
Yeah.
It's all for real value.
yeah.
So what happens for general posets? Like your bounds are much worse because there is no gamma? Or like what did Stanley show?
Oh, you mean, so sequentially differential posets are basically when you you have this equivalence for some Ri and Qi, and this is exactly equal to 0, and then you can run through all this theory and gamma is equal to 0. If you want to do this on a general poset, I mean, the only thing that changes if you have an approximate version is that this 1 over I, what was this coming from? This was coming from the regularity of a simplicial complex. So this comes from the fact that when I move up and then down, I have a 1 over I, my regularity is 1 over I. Really, the only thing that changes is that this becomes the downward regularity of the poset that you're looking at, and then the corresponding eigenvalues, like in the Grossman, you'll get like 1 over Q to the I, which happens to do with if you're over like FQ. The error terms, I mean, they also blow up with this regularity. Like when I relate two things across different levels, there's a blow up by the regularity parameter. So if the regularity is huge, you get a huge blow up in the parameters. Yeah.
Yeah, there's actually an even weaker notion of which is even more general. It still work, yeah.
Okay, so let's take any more questions offline. So let's thank Max again. So we meet again in approximately